Okay, all right. Okay, so what we did last time was we did mean field theory, and what I showed you, we derived it in a way that I'm not going to repeat. We ended up with the mean field equation of state near a critical point, which I'm showing you over here, and uh, and that had that form. We derived it, and then at the end of the lecture, I showed you that we can write that in the form of t to the power beta delta times a function of m over t to the beta, where that function is x plus x cubed over 3. And beta was 1/2, which was the mean field exponent for the order parameter, and delta was equal to 3. Delta for now is just a number. Okay, you've no idea what it means. I'm going to show you what it means in today's lecture, very simply. But that's where we ended last time. And so the implication of this is this: if I take the, instead of making h be a function of m, I make m be a function of h, then what it tells you is that m is a function of h and temperature, function of two variables. But now what we've derived then is that actually it's a function of just one variable, and that one variable is the composite variable which I've drawn over here. That's this variable h over t to the beta delta. So this looks very much like when we were talking about dimensional analysis at the beginning of the class, where we took a function as a function of a bunch of variables, and we turned it into dimensionless variables, and then we saw that those dimensionless variables could be functions of the other dimensionless variables and ratios of them to various powers. So it looks something like that. It looks like the idea that we can reduce the dimensionality of a problem by expressing it in dimensionless terms, and then somehow one of them disappears, and then we are in this reduced dimension where we have sort of a variable of, instead of two variables, everything that depends on now just depends on one variable. So that's where we ended last time. So the question is this the same thing that we would see? So let me show you then, first of all, how it works. So here on the right-hand side is the magnetization scaled in the way that theory predicts, and at the bottom is the temperature scaled in the way that theory predicts. So what do I mean by saying that? So let's have a look over here on the left. So you can see that this equation over here, the one I'm putting a star next to, that equation says that if I plot m over t to the beta, where t is t minus tc over tc, then I plot it as a function of h over t to the beta delta, or equivalently t over h to the power 1 over beta delta, then according to this formula, all those data would collapse onto one universal curve. That's what it says. So let's see, does it work? So you plot it in the way that I've drawn on the right-hand side, and you can see data for various temperatures and various magnetic fields, and they all just falls into one universal curve, which you can see with your own eyes. Actually, this curve is not one magnet, one set of data. This is 5 different magnetic materials, and they're listed in the caption. 5 completely different magnetic materials, and yet when you plot them in the way that we've deduced by mean field theory, actually all these different materials, they all fall onto the same universal curve. They're completely different materials. Some are magnets, some are antiferromagnets even. They fall, some have significant second neighbor interactions, and so on and so forth. They all fall onto the same universal curve, completely different materials. Now, the reason that happens is because all these different materials have one adjustable parameter, which is the critical temperature, Tc. That number is different for each of these materials. But if I scale everything by writing T minus Tc over Tc, my reduced temperature, then in terms of that variable, everything collapses into one universal curve. So this is a fantastic example of universality across different magnetic materials. Now, if you could look very closely, those of you at the front, not only do you see 5 different sets of symbols that are plotted there, you can see a line going through those data points. That line is the prediction from the normalization group theory. It has no adjustable parameters, and it fits the data so well that you can barely see it. Okay. So so this tells you that this data collapse really works. What's plotted there, the exponents beta and delta are not the mean field exponents. They're the exponents that come from the normalization group. If the scaling function is what comes from the normalization group, but the mean field theory got the right idea. It says if you do this, it would work, it just gets the wrong scaling function, it gets the wrong exponent, at least below 4 dimensions. Okay. So let me ask another question. Does this look anything like what happens in dimensional analysis? So in the homework that you just handed in, there was an exercise that some of you may have chosen to do, and that exercise asked you to do dimensional analysis for statistical mechanics. So it said take a bunch of materials, each of which has some sort of potential, say a Leonard-Jones potential, characterized by a binding energy epsilon and an atomic radius r naught, and then show that those class of materials, like rare gases like argon, krypton, xenon, neon, etc., those things, if you plot them, they would all fall onto one universal curve. And you've derived that, those of you who did that question, derived it just from statistical mechanics and dimensional analysis. How many people chose to do that question? One person did.
A little different.
Huh?
It looked a little different. It dealt with Fermi temperature.
Wait. I didn't give you this one. Oh, I took that one off to make it shorter for you guys. Okay, I didn't give it to you. All right, I'll put it on the next one. Okay. And it's super fun. It's amazing. Okay, so you will end up deriving the formula at the bottom here. So this formula at the bottom says this is what happens if you do dimensional analysis. Okay, and you'll derive it. I'll give it to you. So it says if we take the pressure divided by the critical pressure, the volume divided by the critical volume, the temperature divided by the critical temperature, ignore the last thing, the thing with Planck's constant. Ignore that. Okay, that's part of the homework question. Ignore that. It says if you do that, then pressure should, as a function of volume and temperature, should all fall into one universal curve. So let's see if it does. So I'm going to show you that. So let me tell you what you're looking at here. So here is data collapse, but now this is liquid gas. This is not a magnet. Here's a liquid gas curve. The vertical axis is temperature over the critical temperature. So T over Tc. This vertical axis is rho, the density, over rho c. And the density is the number of particles per unit volume. That's what the density is. So that's plotted here. And then this is below the critical temperature. So this is down here is T less than Tc. And when you go below Tc, you know what happens when you compress a gas is it separates into a liquid and a gas that are in coexistence. We talked about that in one of the first lectures of the class. And so if you tell me what is your temperature, like the temperature indicated over here on the left-hand side, then you find that at that temperature, there are two coexisting phases, one at low density, which is the gas, rho g, and one at high density, which is the liquid, rho l. And this graph tells you what they are. And this is the coexistence curve. So this shows you a data collapse, very much like the data collapse shown over here on the left-hand side. And so you might say, this is the same kind of data collapse that we see in critical phenomena. Okay, look at this graph carefully on the screen. Those of you at the front will be able to answer this question better than those of you at the back. Do you think that this curve really is telling you about the critical phenomena data collapse? Yes or no?
Is TC going to be different for each gas? So how are we plotting that?
TC is different for each gas. So when you're doing the experiment, you're measuring the temperature, you're measuring the density, and then rho c is different for each gas, TC is different for each gas. You're scaling, you're making the vertical axis be temperature divided by critical temperature, the horizontal axis be density over critical density, and then you're plotting the data on those axes. Okay, so we've taken out, by doing this, we've taken out hopefully, the material specific aspect of it, and all the data seem to collapse onto one universal curve, right?
So for each gas, you divide it by a different DC.
That's correct.
Like, this will show you what the scaling law is. It's like if you did your scaling law correctly, because your right. You're asking.
I am. I'm asking you, is this kind of scaling the same as this kind of scaling? So the one on the left is the one I showed you, the thing that's derived from the normalization group and experimental data on magnets. The one on the right is experimental data on materials, which are gases, looking at the liquid-gas coexistence. I haven't yet told you what the theory is. So what I'm asking is, do you think that they're the same thing? Who thinks, okay, Gregory.
I think it's not quite the same thing because on the left we have, like, we are changing our axes so that they're with respect to some exponents of other quantity of, in this case, temperature. So we basically are trying to figure out what would be the relationship between the two quantities that would help them follow the same curve. And here we're just having some dimensionless quantities on both axes. And it doesn't tell us much about the scaling between the two.
Okay, so what Gregory is saying is they're not the same. The thing, let me paraphrase what you've said. I think you're right, and let me paraphrase what I think you've said. I think you said the thing on the left is what happens near the critical point. And the thing on the right, if you look at the axes, T over TC is, where I drew the horizontal line, T over TC is about 0.8. The data go down to 0.5. And if you look at the density, it goes from 1 in the middle to 2.6 on the right and virtually 0 on the left. So what that tells you is that those data are not in the critical regime. They're not close to TC. They're not close to the critical pressure. They're not close to the critical volume. These are just data on gases, and they do fall onto one universal curve, but not because of critical point universality. And in fact, this is a consequence of what is called the law of corresponding states. And then in the next homework, I will give you an example for you to work out so that you can derive this yourself. So the one on the left is not an example of critical point scaling. It's a data collapse for a completely different reason. Okay, so you can have data collapses for reasons that have nothing to do with phase transition and critical phenomena. Okay, now there is something super interesting though about this curve. Okay, so this curve was discovered by Guggenheim in 1944, and if you look at on the bottom, let me see if I can expand it without blowing up my iPad. There we go. So he noticed that if I look at the curve very close to the critical temperature, then it looked like the density of the liquid minus the density of the gas over the average density went like 1 minus T over Tc, which in other words is Tc minus T over Tc. It's little t to the power 1/3. Okay, 1/3. Okay, now that's not the exponent that you get from mean field theory, right? In mean field theory, we get a half, beta is a half. But you can see that this curve on the right is asymmetrical. And he noticed this. And so, and he fitted the cubic law through it. And if you remember, I told you that the correct exponent was about 0.326, something like that. And here is a way that the first experimental indication that, yes, there's something weird here. It's not a parabola. It's not a parabola. How the heck is that possible? Okay, so that part of it is a critical phenomenon. Okay, that is, but this whole data collapse outside of the critical regime is not a critical phenomenon. So there's two ways you can get data collapse. Okay, so that will be on the
There seem to be no points on that curve.
Say it again.
There seem to be no experimental data points on that region.
They're all. Yes, he can't get. That's right. You're absolutely right. Thank you. He can't get close to that critical point because that wasn't the purpose of the exercise. He didn't even know about that. But yet, you can see that the data have this asymmetry, and so he was able to fit that. Yes, and it's very difficult to get data points very close to it. There's a whole section in my book about the difficulty in measuring critical phenomena, and I'm not going to go into that now. So let me just summarize what I just told you, and then I'm going to go back up here. So what I just told you. Summary. So this will be on homework 2. I'll put it on for you, and basically the idea is that if I take the pair potential for atoms, so this is the pair potential, the potential energy for 2 atoms I and J, that has the form epsilon times some function of Ri minus Rj over sigma. So this is meant to be the binding energy. This is hardcore radius of the atoms. Excuse me, sorry. That's the hardcore radius of the atoms. And what you will see in homework 2 is that for all materials with the same function u of x and different epsilon and different sigma, their coexistence curve will obey this law of corresponding states. Okay, so that's what we're going. That's what you'll be able to do. And what Guggenheim did was he deduced that rho liquid minus rho gas over rho C scaled like T minus T to the power beta, where beta was roughly 1/3. And that's really quite remarkable. Okay, so now I want to talk about the next topic, which is spatial correlations. So up to now, everything we did was mean field theory. We said every place in the system is the same as every other place. We did a calculation which replaced all of the spins with one representative spin, and we chose it in a self-consistent way, so that representative spin captured the behavior of the whole system. But real systems are not like that. If you do a computer simulation or you do an experiment, you see spatial structure. And we need to talk about spatial structure now in order to properly understand what is happening at a phase transition. And so what we're going to do now is go into a discussion of spatial structure. So I'm going to show you what we mean by spatial correlations. That's how we quantify spatial structure. And then I'm going to derive for you a thing called the static susceptibility sum rule. So I'm going to explain to you the susceptibility that we talked about last time. I'm going to show you that that is related to the correlations in the system, the correlations of fluctuations, and it's by an exact result. And then we're going to talk about the behavior of the correlation length, and we're going to deduce what it behaves like near a critical point because of the way the susceptibility diverges. And in the list here, I've listed the sections in my book and my notes where that material is presented. All right, so let's get started with that. So what is our goal? What we want to do is we want to quantify the spatial heterogeneity. So let me give you an example. Let's suppose I took a snapshot of the system at 2 different times. So let's pretend it's a one-dimensional magnet, or this is meant to be a stand-in for a magnet. So something like that. And then let's suppose I look at some time 9 units later. Then what I might find is I might find some different structure. Something like that. So what we want to understand is that the spatial correlations have changed, and what we want is to know in equilibrium if we average over configurations, what is the probability of observing spin j is equal to +1 given spin I is equal to +1, where Ri minus Rj, the positions, can be arbitrary. So that's the thing that we want to understand. And so now I'm going to show you how we can measure it. Excuse me. Okay, so this is let me give you the number 3.7.2 spatial correlations. And let me define for you a quantity that we're going to hear a lot about in this course, the 2-point correlation function. So the 2-point correlation function is defined like this. It depends on 2 points, I and j, or Ri and Rj, the position of the spin I, position of spin j, and it's defined in the following way. I take the average of Si, Sj, minus the average value of Si and the average value of Sj. So that's how I define this object. And these things over here, this is the location of the spin I, etc. Okay, and these averages here, when I draw these averages, these are thermal averages taken with respect to the Boltzmann distribution. So how do we compute this thing? Well, we know that in principle, what we have to do is literally do an integral. And I'm going to write it down in a minute. But the way we're going to do it is we're going to calculate it by doing differentiation. So the next step then is we're going to calculate by differentiation. Now, I showed you an example of this before, just to compute the magnetization. And this example is a much more useful one, a much more interesting one. So let's see how this works. So let's first of all start off by writing down our Hamiltonian. So our Hamiltonian is minus beta j Si Sj minus beta h sum over I Si. So that's the that's our Ising model Hamiltonian, and I've written it down as e to the minus beta h. So I can write down the partition function. So that is then the trace, which I don't need to write out in full. We know it by now, is the trace of e to the beta j, sum over nearest neighbors, si, sj, plus beta h, sum over I, si. And when I do this, I'm integrating over the si's, so the spins are the dummy variables. They don't appear in the answer. Okay, so if I were to ask the following question, then, so this is just recapping what we did before. Suppose I want to compute the following: the sum from I equals 1 to n of the expectation value of Si. How do I get that? Well, that is by definition 1 over Z, the trace over Si of the sum from I equals 1 to n Si times e to the minus beta times the Hamiltonian. So that is what I will get. This thing is by definition, as we saw, n times the magnetization per spin. So that's how we define it. And you can see that if I were to compute this as a derivative, we did it before earlier, but let me just remind you, what we can do is we can say, if I differentiate the Hamiltonian with respect to this external field H, then that will, because I'm differentiating e to the ax, differentiating with respect to a will bring down the factor x into the ground floor. So this thing is just equal to 1 over beta 1 over z dz by dh, and this is now a function of h and j. So that's what we did before. We saw that the derivative of the free energy with respect to H is just the magnetization. Okay. So this formula is basically dF by dH times 1 over n with a minus sign. Okay, so that's how we can compute the magnetization. Everybody happy about the idea of differentiating through the trace operation and bringing down this variable down to the ground here, which carries with it the sum of S. Everybody happy with that? Anybody not sure what we're doing? Okay, so then let's repeat this. So I'm now going to repeat this. So I'm now going to do, if I repeat it, I'm going to bring down two factors of I and j. So what I would get is the sum over I, the sum over j, si, sj, and that thing is equal to 1 over beta squared, 1 over z, d2z by dh squared. Okay, so I'm differentiating with respect to h again. Remember that the sum over I, si is a dummy variable. So when I call this I here, this I is also a dummy variable. I can call it I can call it j, I can call it hippopotamus if I want. So that's why I get two different sums, I and j equal 1 to n inside that expectation value. Okay, everybody happy with that equation? Anybody have a question about it? Okay, all right, so now watch.
Respect to J.
I could differentiate with respect to j as well, but I'm choosing not to do that. And in one of the homeworks, if I give it to you with the transfer matrix, I get you to do exactly that, a very quick and dirty way to compute these things. Yes, good question. All right, so it looks like everybody is on board. So now let me remind you, the next thing we're going to do is this. We're going to connect this to the isothermal susceptibility that we talked about last time. So let's remember what the isothermal susceptibility is. So M, the magnetization per spin, is -1 over N dF by dH. So we know that that's true. And then we know that the isothermal susceptibility is dm by dH at fixed temperature. And so if I were to write that down, keep that over there on the left-hand side, then chi t is equal to d by dH of m, and m is -1 over n dF by dH. And so that means that this is 1 over n, 1 over beta, d2 log z by dH squared. Okay, so let's write this out a little bit more, slowly. So just skip down from here, if you will. So this is 1 over n, 1 over beta, d by dH of 1 over z, dz by dH. So that's what m is over here, because m, looking on the left-hand side, is equal to this thing. So that's a way to write down what chi is. And now let's do this differentiation. So the differentiation is going to act on two terms in here. One term is the term 1 over z, and then the other term is the term dz by dH. So let's go ahead and do that differentiation using the chain rule. So then this is 1 over n kBt, and then 1 over z d2z by dH squared. All I've done there is take the d by dH and act on the second term, dz by dH. And then I've got to add the d by dH acting on the 1 over z. So the derivative of 1 over z is -1 over z squared times dz by dH. So I get -1 over z squared dz by dH. And then I've got another dz by dH already there. So then it's two factors of that. And then that's the end of the calculation. And now when I look at these two terms, what I can see is that this term over here, d2z by dH squared, this term is equal to this SISJ. And this term over here is just the magnetization squared. So then in putting it all together, what then I end up with is that this is 1 over n, and then 1 over kBt, and then sum I and j, Si, Sj, minus the sum of I, expectation of Si, squared. And this thing is the thing that a few minutes ago I defined for you to be the thing called the correlation function. Now, I haven't told you what the correlation function really measures. We haven't talked about what it, give you a physical intuition about it. I've just defined it, and then I've told you how it's defined, and then I've shown you that what it actually is related to the susceptibility. So let's just see how this is related to the susceptibility. So this is 1 over n, 1 over kBt, and then the sum over I and j, this 2-point correlation function of Ri and Rj. And this result is an exact result. So that's true. So what? Well, let's suppose now that we're in thermal equilibrium. So that means that I'm sampling over all possible configurations of the system. The spins are all fluctuating like this, and I'm computing these averages from the Boltzmann distribution. There's no preferred point in the system. The system is translationally invariant. So if the system is translationally invariant, then that means that it is a function only of this separation between the points I and J. So that means that G of Ri and Rj is actually equal to G of Ri minus Rj. So it's just a function of the difference between them. So whether I take these 2 points and look at the difference between those, or these two and take the difference between those, once I average over all configurations, I get exactly the same results. Question, Andrew?
What did you put the KBT in?
Because it comes in from this term over here. So can you, on the left, can you see where I got the? Okay. So that cancels out. Okay. All right. So then you can say, right, so this is a double sum. This sum over here is a double sum here, and when I say here, I'm looking at this sum. This is a double sum, so I'm going to turn that into a single sum because I'm averaging a variable that is just the same as Ri minus Rj. So I can convert the double sum into a single sum. And it's equal to a single sum times the number of variables, the number of lattice sites, n. And so then what I get is that chi t is equal to 1 over n, 1 over kbt, and then n times, oops, didn't mean to draw that, n times the sum over lattice sites, j equals 1 to n, g of rj. And that is an exact result. And it's called the static susceptibility sum rule. Okay, so the ends cancel out. So chi t is equal to 1 over kbt, and then the sum over sites g of ri. If I now say go from the lattice into a continuum, so I start off with a lattice like that. Let's suppose the lattice spacing is A, the lattice spacing is A, and then I go over into a continuum. So now everything is just some splurge. Then what that means is then I get that chi t is equal to 1 over kbt, the integral ddr divided by the volume of a lattice volume, a unit cell, a to the d, times the 2-point correlation function as a function of r, and that's over the whole system. And this is the thing that's called the static susceptibility sum rule. Yeah, Andrew, did you have a question? A to the d. All right. So what? So in order to understand the so what question, let's first of all understand what is the meaning of the 2-point correlation function. Okay, so you heard about what is the meaning of life, things like this. Now we're going to be physicists. We're going to talk about the meaning of the 2-point correlation function. So it doesn't seem that it means very much, right? It's a bit obscure. We just defined it as this thing, and we just did some algebra, and we got a formula that connects the 2-point correlation function, which we don't know what it means, with the thermodynamic isothermal susceptibility. So now I'm going to show you what it actually means. So to do that, I'm going to rewrite it. So here is our 2-point correlation function, and that is defined as SI Sj minus SI Sj, like so. Now I claim that this thing is the same thing as the following. I take this, write it as SI minus the average of SI times Sj minus the average of Sj. Okay, so I claim that that's the case. And let's just do a quick check. So how do you quickly check it? Well, you have this is equal to SI Sj, that's that with that, and then I have SI times Sj, so I have minus SI times that Sj. So what is the average of 3? It's just the average of 3. So I get that. Then I get another term like this. So I get minus SI Sj. And then I get plus SI Sj, which is this one times this one. So if you do all the combinations, if I've done it right, which it looks like I have, then you end up with the equation that I have up here. So that's a true statement. Now, what does that thing mean to us? Well, that quantity in the first term, remember we defined the fluctuation. We said if you look at the spin SI, it has some instantaneous value. If I look at its average value, that gives me the expectation of SI. And this thing is the thing that I call the fluctuation at the site I. So that's delta SI. And that was the thing that we neglected when we derived the mean field theory. When we did mean field theory, we wrote out the Hamiltonian in a clever way. And then we made it into mean field theory by saying, we're just going to throw away, we're just going to throw away all the fluctuations. And so what that means then is what I've just proven to you is that the 2-point correlation function is the expectation value of the fluctuation SI on the fluctuation Sj. So what this then means is it tells you how much delta SI resembles delta Sj. In other words, if they're completely let's think what could happen. Let's suppose the spin I is over here and spin J is on the other side of the moon. Okay? You would think that if that's the case, if this spin is fluctuating up and down, the one on the other side of the moon is not going to notice anything at all. So what you would expect is that delta SI is not equal to delta Sj if Ri minus Rj has gone to infinity. They're on the other side of the moon from each other. So then if that was the case, then they'd be uncorrelated from each other. And then that would then tell you that that SI, its average, and the average of Sj would be what this thing would turn into. So G would then just be that. So that's what would happen. You could just factorize that probability distribution. So on the other hand, let's suppose that the spins were very close together. So when spin I goes up, then spin J also goes up. When spin J goes down, spin J goes down too, most of the time. So what that means then is that if they're very close to each other, their values are going to be the same. And so that means that then if this is happening, then this means that G is equal to the product of a quantity times another quantity. And these quantities are very similar, which means that G will be large. On the other hand, let's suppose that we're above TC, then where the expectation value of the spins is equal to 0, then that would mean that if Ri and Rj are far apart, that would mean that then G would be equal to 0. So in the case where they're uncorrelated, the average value would be 0, and therefore the correlation function would go to 0. And so what you've learned from this, I'll come to your question in just a second. So what we learned from this is that we would expect that if I were to plot G as a function of distance, it's going to be some number that will then decay in some way at large values. So that's what we would expect. If they're very close together, they're highly correlated. Uncorrelated, far apart. So that's our picture of what G would look like. You have a question?
Yeah. Side goes down.
In the previous equation, which one? The one, this one at the bottom? Uh-huh. So what I'm saying is that the spins are correlated. So if you're imagining watching a movie of the system, let's suppose the spins are far apart. The movie looks like this. This spin is fluctuating like this. This spin has nothing to do with what this one is doing. If on the other hand, they're close to each other, this one flips and this one flips. This one flips, this one flips, like that. So they're more or less doing the same thing. Not all the time, but most of the time. That's all I mean.
So still not deterministic.
Not deterministic, it's all stochastic. This is all in thermal equilibrium. Good. Does that answer your question? Okay, question?
Why is the extent of similarity being measured by the change delta, but not just SI itself?
I could do that too. Okay, but the way I've defined it is not like that. Yeah, and you'll see why later. Okay, you had a question? Same thing?
So I've heard about multi-point correlation functions like 3 and 4. Is that qualitatively different? Like the motivation for that is, I've only ever heard about it. I don't really get why.
So the question was, there are these things called multi-point correlation functions. So here's a 2-point correlation function of 2 points in space. I can have a 3-point correlation function, 4-point correlation, 5-point correlation, and so on and so forth. So the question was, who cares about those things, right? Right. So the answer is this. Let's suppose I told you I've got a probability distribution, and I said I can calculate for you the mean. Okay, great. I can calculate for you the standard deviation. Okay, and then I say to you, I can calculate the standard deviation is just the expectation value of x squared times the probability distribution, right? So it's just the second moment of the distribution. Well, you could say, well, if the distribution is a Gaussian, that's all I need. But if it's not a Gaussian, then I could say, what is the expectation value of x cubed, x the fourth, and so on and so forth. And those things would be different. They wouldn't just be the mean and the standard deviation.
And what would that look like? Would that also,
Well, it would let you,
would it be like just a product of multiple?
yes, so it could be just a product of multiple SIs and SJs. So now you're looking at higher moments, but also distributed in space. And then there's lots of ways that you can distribute those things and subtract things and so on and so forth. And in many body theory, you do calculate those things. What we're going to do is mostly not calculate them. But at the end of the course, when we talk about how to do Feynman diagrams and so on, we will in principle see how to calculate all those things, and they matter. And the reason they matter is near a critical point, the distributions are not Gaussian. All right. So all good questions, but I'm afraid we're going to have to move on. So this is roughly the intuition about what this function tells you. Basically, when it's big, it means that those degrees of freedom are correlated, they move in step probabilistically, and if it's small, then they're not moving in step. If I draw you a curve like this, and I say, what is that function? For a physicist, there's only one function. So you might guess that this function, this g of r, is proportional to e to the minus r, because that's what it looks like. And in fact, it does go like that, but r has got dimensions. So if r has dimensions, then to make it dimensionless, I have to divide by another length scale, and that length scale is called psi, and that's called the correlation length. So this is called the correlation length. And you need it in order to make this thing, make the exponential dimensionless. So if I draw that on my curve over here, roughly speaking, I don't know, something like this is what I mean by the correlation length. So it sets the scale for how long it takes for the correlation length to decay by 1 over e. That's what it means. Okay, so that will be what you would guess, and in fact we will see that we can actually compute this precisely. So a real calculation, which I'll show you how to do later, a real calculation gives you that g of r looks like this. When r is much larger than the correlation length, this actually goes like e to the minus r over psi divided by r to the power d minus 1 over 2 times the correlation length times d minus 3 over 2. So if I've copied this down right, then that's the correct formula for the asymptotics of the two-point correlation function. And this is true when t is not equal to tc. Okay. All right, so that's the asymptotics. Okay, so now I want to go back to the static susceptibility sum rule. Okay. Reclaiming host. Hi there. Really sorry, our call got cut off, so we have to restart it. Start the broadcast, and presumably I need to start recording again. Pause recording, stop recording. So it's still recording. Okay, great. Okay. All right. What the heck happened? All right. So now let's go back to the static susceptibility sum rule. Static susceptibility sum rule implies So I showed you that chi is equal to 1 over the lattice spacing to the dth power, 1 over kbt times the integral over space of the 2-point correlation function, like that. Okay, so now here is the puzzle. Here is the thing that should make you very concerned. This thing we proved last time that chi, at least in mean field theory, goes like 1 over kb t minus tc, at least for t greater than tc. And in the homework, I think you calculated what happens below tc, right? Yeah, okay. And you got the same result, different coefficient, right? You got a factor of 2 different. Everybody get that? Okay. If you didn't, we'll correct your homework for you. All right, so what that means is that this thing diverges with an exponent minus gamma, and gamma in mean field theory is equal to 1. All right? So we know that this quantity, pi, can go to infinity. But we have a real problem here, because if I look at the integral ddr of g of r, this thing is always convergent. Why is it convergent? Well, it's convergent because this g of r goes like e to the minus r over some correlation length, so it converges exponentially at infinity. If it converges exponentially at infinity, then this integral is convergent. So what I've just shown you is that the left-hand side can diverge as t tends to tc. The right-hand side is always convergent. So we have a problem. Okay, the left-hand side does not equal the right-hand side. So we have a paradox. And that's the thing that we need to resolve. Okay, so anybody got any ideas about what's going wrong here? Thermodynamics told us that the susceptibility has to diverge. Thermodynamics and an exact identity told us that the susceptibility is exactly related to an integral of the 2-point correlation function. The 2-point correlation function really does decay exponentially, and therefore, when I do the integral, it has to be convergent. So the integral of g is convergent, but chi on the left-hand side can diverge as t goes to tc. The left-hand side is not equal to the right-hand side, so we have a problem. So how do we resolve that problem?
Gamma MFT is incorrect.
Say it again.
Gamma MFT is incorrect.
Well, even if the gamma was not 1 but was 17, it would still be diverging. Okay, somebody else, Gregory. Yeah, yeah, you know the answer. Okay, if I ask you guys a question, and you're not that you know the answer, but you know the answer, then don't answer because because then I can tell you that as well. Okay, all right. Because I asked the question because I want to get the class to think that the people are seeing it for the first time. Okay, so the only way this can happen is if this correlation length itself goes to infinity. So if psi goes to infinity, then it can be the case that the integral does not converge. So the only way this can happen is if the correlation length must go to infinity as t tends to tc, so that the integral does not converge. That's the only way that this can happen. And let's think about that, because look on the left-hand side. On the left-hand side, I was very careful to explain this approximation over here, the asymptotic approximation. I showed you when it is true. It is true when R is much larger than the correlation length. It's the exponential decay, okay? If the correlation length is going to infinity, then R can never be bigger than the correlation length. So then we must be in a different regime of this correlation function. So what I've shown you over here on the left-hand side, this asymptotic formula for the correlation function is only true for R greater than psi. It's not true when R is much smaller than psi. And if the correlation length has gone to infinity, then R necessarily has to be smaller than psi. And if R is smaller than psi, then the integral will not converge. And if the integral doesn't converge, then the integral on the left, the term on the left-hand side and the integral on the right-hand side have a chance to be equal. So that's the idea. So the integral doesn't converge. And so the idea is that the integral does not converge, which means that as t goes to tc, R cannot be bigger than psi. Okay, so let's try to do the integral. Okay, let's try to work out. So then the question is, how must psi diverge as t goes to tc in order that the left-hand side equals the right-hand side? So we can work this out by reverse engineering. We know the left-hand side diverges as 1 over t minus tc, at least in mean field theory. So now we can ask, what is the dependence of the divergence of the correlation length as t goes to tc that will make the left-hand side equal the right-hand side? So here's how we do the calculation. We just say that t minus tc over tc to the minus 1. I'm going to ignore all the factors of Boltzmann's constant and 2 and things like that just for now. So now we're going to do this integral on the right-hand side. So this is the integral ddr of g of r, the 2-point correlation function. And if I write that in spherical polar coordinates and pretend that this function really is just going as an exponential, then what I would get is the surface area of a unit d-dimensional sphere, then the integral from 0 to infinity dr, r to the d minus 1 dr, e to the minus r over psi divided by these factors, r to the d minus 1 over 2, psi to the power d minus 3 over 2. So that's just plugging that in and doing the integral in radial coordinates. So this thing here is the surface area of a unit d-dimensional sphere. Sphere of radius 1 in d dimensions. And there's a really, really cool trick to work out what that is, okay? And I'll tell you what that is. But let's, for the moment, not worry about that. It's just a number. It's 4 pi over gamma over d over 2 or something like that, where gamma is the Euler gamma function. So let's just work out, never mind about the factors of pi and so on. Let's just do this integral. So if I make the change of variable, z is equal to r over psi, then this integral turns into the following: t minus tc over tc to the minus 1 is then equal to the surface area of the d-dimensional unit sphere. I've made a change of variable, so you have to now follow through the factors of d and so on. So what you get is psi to the power d. Sorry, I got that wrong. Psi to the power 2. And then you have the integral 0 to infinity of z to the power d minus 1 over 2 e to the minus z dz. Okay, so look at what happened here. I made this change of variable, z is r over psi. In fact, r over psi is exactly what is there, and then all the other terms are powers of r. So when I make that change of variable, what ends up happening is I just do the change of variable, I get powers of psi. So you do the algebra, and what you find is I get 2 powers of psi out in front, and then I get this thing in the middle, and this thing in the middle here, this thing here, this integral, this is just a number. Okay, there's nothing else in it, it's just a number. It's 17 or something like that. Okay, whatever it is, just a number. So I don't care about it. And so then what I've got then is that psi squared diverges as t minus tc to the power minus 1. And so then this then implies for me that the correlation length as a function of temperature must diverge as t minus tc over tc to the minus nu, and nu has to equal 1/2 in mean field theory in order for this to be consistent. So if nu is equal to 1/2, the correlation length diverges as t minus tc to the minus 1/2, then what will happen is then I will satisfy the static susceptibility sum rule. So then if this is true, then this implies that the static susceptibility sum rule is satisfied. And it needs to be satisfied because it's exact. So it can't be violated. Okay, so just to recap, so what we discovered then is because of the way that the divergence of thermodynamics thermodynamic quantity, which was isothermal susceptibility, that implies a divergence of the spatial correlation length. And all of this is using mean field theory results. So we know that new mean field theory is not correct. We know it's a slightly different number. I told you what the real one is in 3 dimensions last lecture. So we know that the nu is 1/2 is not going to be exact either. It's going to be some other number. It won't be 1/2, but it'll be something that you can work out. But basically, we've now got we've now reconciled the thermodynamics and the spatial correlations. Now, there's one thing that we haven't talked about. So the last remaining question then is what happens exactly at Tc? Okay, well, we know it can't be exponential, and the answer is that it's a power law. So the answer is this: G of R evaluated at T is exactly equal to Tc. That behaves like some number times 1 over R to the power D minus 2 plus eta. So it goes as a power law decay. Power law, not exponential, decay with distance. And what that exponent is depends on the spatial dimension, but it also depends on eta. And what is eta? Eta is a new critical exponent. introduced by Michael Fisher originally. So that's a new exponent that we have to figure out what it is. And I'm going to replace this equal sign with a proportionality sign just to be precise. Okay, one second here. I want to just finish what I'm saying. So if I now look at the picture, so what basically the way to think about this is when I'm away from the critical temperature, there is a length scale over which correlations decay. As I go to the critical temperature, that length scale has gone to infinity. That means it goes out of the dimensional analysis. Okay, so now I've got no length scale. So what that means is that at t equals tc, there is psi is equal to infinity. So there's no scale for spatial fluctuations. And that means that there's no scale. So that means the system is now scale invariant. It has scale symmetry. It's fractal. Okay. All right. So then I want to draw for you what the correlation function really looks like. Andrew, you had a question?
I was just gonna ask, maybe I blanked or something, but you didn't really offer much of a physical description of what the correlation is.
I did. I explained to you that it's the length over which the fluctuations look the same. Okay.
I did.
You did blink. All right. So now let's now recap, and let's rewrite the functional form of the correlation function. So a few pages ago, I said that it looks like an exponential, but now you probably realize that that's not quite correct, because I told you that the exponential behavior was only true asymptotically. In fact, later we will solve it exactly in a version of mean field theory which includes fluctuations, small fluctuations, and we'll see that it turns out to be a thing that we can exactly solve. It's a modified spherical Bessel function of the third kind, okay, or a Macdonald function. So those of you who are time travelers from the 19th century, you'll be very happy with the normalization group and so on, because a lot of it is doing a lot of applied math, solving equations and using special functions and so on. So that's what it is. So let me show you what's really going on here. So here is R. I'm doing the unconscionable thing of drawing R as the horizontal axis, as if R has no dimensions. But R really does have dimensions, and it's not correct to write it as R. So really, it should be R over the lattice spacing. Okay. So in units of the lattice spacing, A, here is my correlation length over here. And now what we saw and we argued was that the correlation length, so the correlation function is decaying exponentially when R is larger than this correlation length. When R is smaller than this correlation length, we didn't say what it is, but I'll tell you what it is. It basically looks like this. It's coming in sort of like that. And this behavior over here, is going as 1 over R to the power D minus 2 plus eta. And then there's over in this range, there's some sort of crossover between the R goes to 0 and R going to infinity asymptotics. So that's what it looks like. And so this is a slow decay with distance, and then this is a fast decay with distance. Okay, so let's then now ask, how do I know that this picture is correct? And we know it is correct because what's happening is the following. Let's suppose that you tell me that I'm going to measure the 2-point correlation function at a particular point in space, particular distance in space. And that distance in space is over here. So let's call this let's say call it R naught. Okay, so let's suppose that that we're over here and we measure at that distance in space. Next, let's imagine that we now take T and move it towards TC, let's say from above. So then what's going to happen is that psi is going to get larger. Maybe it's not going to equal infinity, but it's going to be larger. So now what my picture is going to look like is going to look like this. Here is my point R naught, but now what's happened is my correlation length has gone out to a much larger value. So this behavior is going like that, and then here is the exponential decay. And the psi is now over here. So now I've gone from a regime where R naught is much bigger than psi to a regime where R naught is much less than psi. And so I'm looking at the correlation function in a different asymptotic limit of its argument. So it's not that some function changed from being exponential to power law just magically. What happened was I had the same function all along, but what happened was I looked at the part of the function, a different part of the function, when I'm above TC, when I'm way away from the critical point, and then when I'm close to the critical point. And so this picture is true when T is very close to TC, and this picture is true when T is, say, much bigger than TC. All right, so I think that's where we're going to stop for today. So so let's see, is there anything else that I wanted to explain to you? Yes, there are a few more things, but I'm not going to do them today. So so we will leave it there. So what I've told you today is that thermodynamics is intimately connected to spatial correlations. The divergences of thermodynamic functions tell you that spatial correlations also behave strangely near critical points. We've learned that there is a length scale associated with spatial correlations, and we've learned how it behaves as you get close to the transition. And we've learned that the thing that connects the thermodynamics and the correlations is the static susceptibility sum rule, an exact identity that tells you how the thermodynamics are integrals over space of spatial correlations. Okay, so we'll leave it there for today, and we'll pick it up again on Thursday. Hang on 1 second.